There's something you need to know about the universe. It remembers, not the way you remember, imperfectly, selectively, with gaps and distortions that grow larger over time. The universe remembers completely, permanently, without error or omission. Every photon that ever shone, every atom that ever vibrated, every thought that ever flickered through a conscious mind. It's all still there, encoded in the deepest structure of reality, preserved at the boundary of existence itself. This is the holographic principle, and it changes everything about how we understand what's real. The idea emerged from a crisis in physics. Black holes seem to destroy information, to erase things from existence permanently. But quantum mechanics says that's impossible. Information must be conserved like energy. Can change form, but it can never truly disappear. The resolution came from an unexpected place. Physicists discovered that all the information falling into a black hole gets encoded on its surface, on the two-dimensional event horizon, like data written on a spherical hard drive. Nothing is lost. It's just stored differently. And if black holes preserve information this way, maybe the whole universe does too. Maybe everything that ever happens gets written on a cosmic boundary at the edge of reality. Maybe the three-dimensional world you experience is a readout, a holographic projection of information stored on a distant two-dimensional surface. Maybe right now, as you lie there in the quiet darkness, every detail of this moment is being recorded forever. Tonight, we explore the universe that never forgets, and we ask what it means for existence, for memory, for the moments that make up a life, that nothing is ever truly lost. We'll begin with one of the most terrifying objects in the cosmos, a place where space and time break down, where matter is crushed to infinite density, and where, for decades, physicists believed information went to die. We'll discover how this cosmic monster led to a revolution in our understanding of reality. And we'll follow that revolution to its most profound conclusion, that you and everyone you've ever loved, and every moment you've ever lived, might be eternally preserved in the fabric of existence itself. Let's begin with the black hole, the devourer, the eraser, the object that turned out to be, against all expectations, the universe's most perfect memory. Before we can understand how black holes preserve information, we need to understand what black holes actually are. And they are, without exaggeration, the strangest objects in the known universe. A black hole forms when a massive star dies. Throughout its life, the star has been engaged in a constant battle, the outward pressure of nuclear fusion pushing against the inward pull of gravity. For millions or billions of years, these forces balance perfectly. The star shines steadily, converting hydrogen to helium in its core, then helium to carbon, carbon to oxygen, and so on up the periodic table. But eventually, the fuel runs out. When a star massive enough, about 20 times the mass of our sun or more, exhausts its nuclear fuel, the outward pressure that held it up vanishes in an instant. And gravity, patient and relentless, finally wins the battle it has been fighting since the star was born. The collapse happens with terrifying speed. In less than a single second, the core of the star implodes. Matter falls inward at a significant fraction of the speed of light. The density increases beyond anything we can imagine. Electrons are crushed into protons to form neutrons. And if the mass is great enough, even the neutrons, packed together as tightly as the laws of physics allow, cannot withstand the pressure. The matter keeps falling, compressing, concentrating into a smaller and smaller region of space. Eventually, so much mass is packed into so small a volume that the escape velocity, the speed needed to break free of the gravitational pull, exceeds the speed of light itself. And since nothing in the universe can travel faster than light, nothing can escape. Not matter, not radiation, not even light itself. The object has become a black hole. The boundary of this region is called the event horizon. It's not a physical surface. There's no wall or barrier you could touch if you approached it. It's simply the point of no return, the mathematical surface marking where escape velocity equals the speed of light. Cross it and you will never come back. No force in the universe, no matter how powerful, can save you. You are cut off from the outside universe forever. Inside the event horizon, things get even stranger. The mathematics of general relativity, Einstein's theory of gravity, predict that all the infalling matter gets crushed into a single point of infinite density called a singularity. At this point, density becomes infinite, spacetime curvature becomes infinite, and our equations break down completely. We don't know what actually happens at the singularity. The laws of physics as we understand them simply stop working. From outside, a black hole is eerily simple. It can be completely described by just 3 numbers: its mass, its electric charge, and how fast it's spinning. Nothing else matters. 2 black holes with the same mass, charge, and spin are absolutely identical in every measurable way, regardless of what fell into them or how they formed. A black hole made from a collapsing star looks exactly the same as one made from collapsing elephants, or collapsing libraries, or collapsing civilizations. All the complexity, all the information about what went in, it's all hidden behind the event horizon, inaccessible to the outside universe. This is sometimes called the no-hair theorem. Black holes have no hair, no distinguishing features beyond those 3 basic properties. Physicist John Wheeler summarized it memorably: black holes have no hair. For decades, this seemed to be the complete story. Black holes were exotic and fascinating objects, but they were also strangely simple. Things fell in and they were gone. The black hole grew a little more massive, perhaps gained a little charge or spin, and that was that. The universe's ultimate garbage disposals, swallowing everything without a trace. Then came Stephen Hawking with a discovery that would turn this comfortable picture completely upside down. In the early 1970s, Stephen Hawking was trying to understand how quantum mechanics, the physics of the very small, behaves in the extreme environment near the event horizon of a black hole. It was meant to be a straightforward calculation, applying well-understood quantum principles to a well-understood gravitational situation. Instead, it became one of the most important and unsettling discoveries in 20th century physics. Hawking found that black holes are not truly black. They glow. To understand why, we need to appreciate one of the strangest features of quantum mechanics: the uncertainty principle. This fundamental law tells us that even completely empty space, a perfect vacuum with no particles at all, is not truly empty. It seethes with activity at the quantum level. Pairs of virtual particles constantly pop into existence and then annihilate each other, all within a time span so short that it doesn't violate conservation of energy. These aren't real particles, they're quantum fluctuations, temporary ripples in the underlying fields that fill all of space. Near the event horizon of a black hole, something unusual happens to these virtual particle pairs. Normally, a particle and its antiparticle appear together from the vacuum, exist for an immeasurably brief instant, and then collide and annihilate each other, returning their borrowed energy to the vacuum. But right at the event horizon, one member of the pair can fall into the black hole while the other escapes into space. The escaping particle becomes real. It carries energy away from the black hole and can be detected by a distant observer. And since energy must be conserved, this energy has to come from somewhere. It comes from the black hole itself. The black hole loses a tiny amount of mass every time a particle escapes this way. This is Hawking radiation. It means that black holes are not eternal. They slowly evaporate particle by particle over unimaginably long time spans. A black hole with the mass of our sun would take about 10 to the 67th power years to evaporate, far, far longer than the current age of the universe. But given enough time, any black hole will eventually disappear completely, vanishing in a final burst of radiation. This was a remarkable discovery on its own. It connected quantum mechanics, gravity, and thermodynamics in a completely unexpected way. But Hawking quickly realized that it created a devastating problem for physics. The radiation emitted by an evaporating black hole is thermal. It's random, like the heat radiating from a warm object. Carries no information about what fell into the black hole. It's exactly like the heat rising from a fire. It tells you nothing about what was burned. So here's the puzzle. When a black hole evaporates completely, where does all the information go? Think about everything that could fall into a black hole over the billions or trillions of years of its lifetime. Stars, planets, asteroids, comets, spacecraft, perhaps even entire alien civilizations with all their accumulated knowledge and history. Every single atom of every single object contains information about its quantum state, the positions, momenta, spins, and quantum entanglements of all its constituent particles. This information is what makes a thing what it is. It's what distinguishes one configuration of matter from another, what makes a book different from a rock different from a brain. When objects fall into the black hole, this information falls in too. It's trapped behind the event horizon, inaccessible to the outside universe, but presumably still there, still existing in some form inside the black hole. But then the black hole evaporates. It converts all its mass into random, featureless thermal radiation and disappears. And once the black hole is gone, the information has nowhere to be. Is it simply destroyed, erased from existence, gone forever, as if it had never been? If so, then something is terribly wrong with our understanding of physics. One of the foundational principles of quantum mechanics is called unitarity. It's the requirement that information is always conserved, that quantum evolution is reversible. In principle, if you know the exact quantum state of a system at any moment, you can calculate what it was at any time in the past and what it will be at any time in the future. Information is never created and never destroyed. It can be transformed, scrambled, spread out, encoded in different forms, but it can never be lost. If black holes violate unitarity, if they genuinely destroy information, then the entire mathematical framework of quantum mechanics becomes inconsistent. Probabilities stop adding up to 100%. Predictions become impossible. The most successful and precisely tested theory in the history of science falls apart at its foundations. Hawking, characteristically bold and willing to challenge conventional thinking, initially argued that this is exactly what happens. Black holes are special, he said. They really do destroy information. Quantum mechanics needs to be modified to accommodate them. The loss of information in black holes, he proposed, is just a fact about nature that we have to accept, uncomfortable as it might be. Most other physicists were horrified by this conclusion. To abandon unitarity would be to abandon quantum mechanics itself, to throw away the framework that underlies all of modern particle physics, chemistry, and our understanding of matter itself. There had to be another explanation. The information had to be preserved somehow, even if we couldn't see how. This disagreement between those who believed information is genuinely destroyed and those who believed it must somehow escape became known as the black hole information paradox. It would dominate theoretical physics for the next 3 decades, driving some of the deepest and most creative thinking about the nature of space, time, and reality. And its resolution would come from a completely unexpected direction, one that would reveal something profound about the fundamental structure of the universe itself. While physicists argued about whether information survives or is destroyed by black holes, another puzzle was quietly developing, one that would point the way toward the ultimate resolution. In 1972, a young physicist named Jacob Bekenstein was thinking about the second law of thermodynamics. This is one of the most fundamental laws in all of physics. It says that entropy, a measure of disorder or equivalently of missing information, always increases in any closed system. You can scramble an egg, but you can't unscramble it. Heat flows spontaneously from hot objects to cold ones, never the reverse. The universe as a whole moves relentlessly and irreversibly toward higher and higher entropy. But Bekenstein noticed a problem. What happens if you throw a high-entropy object, something with a lot of disorder and missing information, into a black hole? The object crosses the event horizon and disappears from the outside universe. Its entropy seems to simply vanish. But this would violate the second law. Entropy can't decrease. Where did it go? Bekenstein proposed a radical answer. Black holes themselves have entropy. In fact, they have enormous amounts of it, more entropy per unit volume than any other object in the universe. When something falls into a black hole, its entropy doesn't disappear. It gets added to the entropy of the black hole itself. But here's what made Bekenstein's proposal truly revolutionary. He didn't just say black holes have entropy. He calculated how much, and his answer was deeply strange. The entropy of a black hole, Bekenstein discovered, is proportional to the surface area of its event horizon. Not the volume inside the horizon, the area of the boundary. This is bizarre. Think about any ordinary object, a room, a box, a container of gas. The amount of stuff you can fit inside, and therefore the amount of entropy or information it can contain depends on its volume. A bigger room holds more furniture. A larger container holds more gas molecules. Capacity scales with volume. But black holes don't work this way. A black hole with twice the radius doesn't have 8 times the entropy. It has only 4 times the entropy because its surface area has increased by a factor of 4. The interior volume seems to be irrelevant. All that matters is the boundary. A few years later, Stephen Hawking confirmed Bekenstein's intuition from a completely different direction. By calculating the temperature of black hole radiation, he was able to derive the exact formula for black hole entropy. What emerged is now called the Bekenstein-Hawking formula. The entropy of a black hole equals 1/4 of the event horizon area, measured in fundamental Planck units. Let me give you a sense of what this means numerically. The entropy measures how many different microscopic configurations could produce the same macroscopic black hole. A black hole with the mass of our Sun would have an entropy of about 10 to the 77th power. That's a 1 followed by 77 zeros. For comparison, all the ordinary matter in the entire observable universe, every star, every planet, every gas cloud, has a total entropy of roughly 10 to the 88th power. A single solar mass black hole contains nearly as much entropy, as much hidden information, as everything else we can see. Black holes are not simple objects at all. They are the most information-dense things in the universe. But the truly strange thing, the thing that would lead to a revolution in physics, is that this information content scales with area, not volume. Think about what this means. If you want to know the maximum amount of information that can be contained in a region of space, you don't look at the volume of that region. You look at its surface area, at its two-dimensional boundary. The interior is somehow redundant. In some deep sense, everything that can be known about the inside is already encoded on the outside. This was the first whisper of what would become the holographic principle. The idea that all the information about a three-dimensional region of space can be fully encoded on its two-dimensional boundary. The interior is real, but it's not fundamental. It emerges from the boundary. Before we go further into the physics, let's make sure we understand what hologram means. Because when physicists say the universe might be a hologram, they don't mean it's fake or illusory. They don't mean we're living in a simulation or that nothing is real. They mean something much more specific and much more strange. You've probably seen holograms before. The most common kind appear on credit cards and driver's licenses. Shimmery, rainbowed images that seem to have depth even though they're printed on flat plastic. More impressive holograms show up in museums and art galleries. Full three-dimensional images that you can walk around, that show different perspectives from different angles, that seem to float in space like real objects. A hologram looks three-dimensional, but it's produced entirely from information stored on a two-dimensional surface. That's its defining feature. And the way this works is fascinating. When you take an ordinary photograph, you record the intensity of light at each point. Bright areas of the scene show up as bright spots on the film. Dark areas show up as dark spots. You end up with a flat, two-dimensional representation of a three-dimensional scene. All the depth information is lost, collapsed into a single plane. A hologram does something more clever. It records not just the intensity of the light, but also its phase, the timing of the light waves as they arrive at the recording surface. To do this, you need coherent light, which is why holograms are made with lasers. The laser beam is split in two. One half illuminates the object you want to record, and the other serves as a reference beam. When these two beams meet at the recording medium, they create an interference pattern, a complex pattern of light and dark fringes that encodes both the intensity and the phase of the light from every part of the object. When you later illuminate this interference pattern with appropriate light, something remarkable happens. The pattern reconstructs the original light waves, complete with all their phase information, and you see a full three-dimensional image. You can move your head and see different perspectives. The image has genuine depth and parallax. You could take a photograph of it from different angles and get different pictures. All that three-dimensional information was stored on a flat piece of film. The film doesn't contain a three-dimensional object. It contains a two-dimensional pattern that encodes three-dimensional information in a way that can be reconstructed by shining light through it. The holographic principle in physics is exactly analogous. It proposes that the universe works the same way. All the information about what happens in a three-dimensional region of space, the principle says, is fully encoded on the two-dimensional boundary of that region. The interior of the region, with all its depth and distance and volume, is like a holographic image, real and tangible and measurable, but ultimately derivative. The fundamental reality is the information on the boundary, and the three-dimensional interior emerges from it. This doesn't mean the interior is an illusion. The three-dimensional world you experience is completely real. You can move through it, touch things, make measurements, but it might not be the deepest level of reality. The boundary might be more fundamental, with the interior emerging from the patterns of information encoded there, just as a holographic image emerges from the interference pattern on a piece of film. And here's why this matters for our story tonight. If everything that happens in a region of space is encoded on its boundary, then every event is recorded. Every moment is preserved. The boundary is a memory, a complete, perfect, permanent record of everything that occurs within it. The universe doesn't just happen to remember, can't forget. Every event writes itself into the fundamental structure of reality and stays there forever. For many years after Bekenstein and Hawking's work, the holographic principle remained an intriguing idea but little more. There was circumstantial evidence, the mysterious area scaling of black hole entropy, but no concrete, rigorous example of how holography would actually work. It was a tantalizing hint, not a proven fact. That changed dramatically in 1997, when a young physicist named Juan Meldacena made a discovery that would transform theoretical physics. Meldacena was working in string theory, the theoretical framework that attempts to describe all particles and forces as vibrations of tiny, one-dimensional strings. String theory is mathematically beautiful but notoriously difficult to test, since the strings themselves are far too small to observe directly with any conceivable experiment. To make progress, theorists often study string theory in simplified settings, idealized universes that are mathematically tractable even if they don't look exactly like our own. One such setting is called Entanglement space, or ADS for short. This is a space-time with a very specific kind of geometry. It has constant negative curvature, meaning it curves away from itself at every point, like an infinite saddle shape or a Pringle chip extended in all directions. Unlike our universe, which appears to be flat or very slightly positively curved, ADS space is hyperbolic. It also has a boundary, a surface at infinity that wraps around the entire space, infinitely far from any interior point. Meldacena studied string theory in five-dimensional ADS space. This is a universe with 4 spatial dimensions plus time, curved in the specific anti-de Sitter way. It doesn't look like our universe at all. It has the wrong number of dimensions, the wrong curvature, and it's not expanding. But its mathematics is beautiful and tractable, and Meldacena made an astonishing discovery about it. The string theory living in the five-dimensional ADS interior, the bulk, is completely, exactly, precisely equivalent to a different theory living on the four-dimensional boundary. Let me emphasize what equivalent means here. Not similar, not approximately the same, not related by some complicated transformation. Exactly, precisely, mathematically identical. They are 2 different descriptions of the same physical reality, 2 different languages for expressing the same facts. And the boundary theory is much simpler than the bulk theory. It's a type of quantum field theory, similar to the theories we use successfully to describe particles and forces in our own universe. And it has one remarkable feature. It has no gravity. Gravity exists in the five-dimensional bulk, but not on the four-dimensional boundary. This is what Meldacena discovered. A complex theory with gravity in 5 dimensions is exactly equivalent to a simpler theory without gravity in 4 dimensions. Everything that happens in the higher dimensional bulk can be perfectly described by physics on the lower dimensional boundary. This is like saying that a full-length movie, with all its motion and action and sound and duration, is exactly equivalent to a single photograph. Every car chase, every explosion, every line of dialogue, somehow encoded in a single static image. Not just related to it, exactly the same thing. This correspondence, called ADS/CFT, where CFT stands for conformal field theory, is holography made rigorous. It's a precise, mathematically proven realization of the holographic principle. The three-dimensional bulk, with all its gravity and complexity, is a holographic projection of information encoded on the two-dimensional boundary. Now, I should be clear, our universe isn't anti-de Sitter space. Our space-time has different geometry. It's approximately flat and it's expanding, whereas ADS is negatively curved and static. So Meldesena's specific correspondence doesn't directly apply to the cosmos we inhabit. But the general principle almost certainly does. If holography works so precisely and beautifully in one setting, if the bulk really does emerge from the boundary, then something similar is probably true in general. The message of ADS/CFT is that our intuitions about space are wrong. Three-dimensional reality can be encoded on two-dimensional boundaries. Space can emerge from information. The interior is not fundamental. And if this is true for our universe, then everything that happens is encoded on some cosmic boundary. Every event, every moment, every configuration of matter and energy, all of it recorded and preserved. The universe is a hologram, and a hologram remembers. The ADS/CFT correspondence tells us that holography works, that the bulk really does emerge from the boundary. But it doesn't tell us how. How can information on a flat, two-dimensional surface give rise to the experience of depth and distance and three-dimensional space? What is the mechanism? The answer turns out to involve one of the strangest and most profound phenomena in all of quantum physics: entanglement. You may have heard of quantum entanglement before. Einstein famously called it spooky action at a distance, and he meant it as a criticism. He thought it showed that quantum mechanics must be incomplete. But decades of experiments have confirmed that entanglement is absolutely real. It's one of the most thoroughly verified phenomena in physics. Here's what happens. When two particles interact in certain ways, they can become entangled, linked together in a quantum correlation that persists no matter how far apart they travel. Once entangled, measuring one particle instantly affects what you'll find when you measure the other. For example, create two photons in an entangled state, then send them flying off in opposite directions. One goes to a laboratory on Earth, the other to a laboratory on Mars. When the Earth scientist measures her photon's polarization and finds it's vertical, she instantly knows with certainty that the Mars photon's polarization is horizontal. Not because any signal traveled between them, but because they were entangled from the start. This seems to violate relativity. How can information travel faster than light? But actually, it doesn't. You can't use entanglement to send messages, because you can't control what result you'll get when you measure your particle. All you can do is learn a correlation. The influence isn't really influence at all. It's correlation, built into the particles when they were created and maintained regardless of distance. Entanglement is strange. It connects particles across space in a way that has no classical analog. But here's what makes it revolutionary for our story. In recent years, physicists have begun to suspect that entanglement doesn't just exist within space. Entanglement may be what creates space. In 2006, physicist Mark van Ramsdonk proposed a radical idea. Working within the ADS/CFT correspondence, he argued that the geometry of the bulk space, its shape, its distances, its curvature, emerges from patterns of entanglement in the boundary theory. Here's the key insight. The more entangled two regions of the boundary are, the closer together the corresponding regions in the bulk. Think about what that means. Distance, the space between things, the separation between here and there, isn't fundamental. It emerges from quantum correlations. Two points are close together in the bulk because the corresponding regions of the boundary are highly entangled. They're far apart because the entanglement between those boundary regions is weak. Space itself might be woven from entanglement. Van Ramsdonk illustrated this with a beautiful thought experiment. Imagine a holographic universe, bulk space emerging from a boundary. Now imagine dividing the boundary in two, like cutting a piece of paper in half. The two halves start out maximally entangled with each other. What happens to the bulk space? As long as the boundary halves are fully entangled, the bulk is connected, one continuous space. But now imagine gradually reducing the entanglement between the two halves. The bulk space responds. A thin bridge forms between two regions that are pulling apart. The bridge gets longer and thinner as the entanglement decreases. Eventually, when all entanglement between the boundary halves is removed, the bridge pinches off completely. The space splits into two separate, disconnected pieces that have no connection to each other. Entanglement holds space together. Remove the entanglement and space-time falls apart. This idea that geometry emerges from entanglement has gained significant support in recent years. It's sometimes expressed in a slogan proposed by Juan Meldacena and Leonard Susskind, ER equals EPR. ER refers to Einstein-Rosen bridges, wormholes, connections through spacetime between distant regions. EPR refers to Einstein-Podolsky-Rosen pairs, entangled quantum particles. The conjecture is that these two things, which seem completely different, are actually the same phenomenon. Wormholes are entanglement. Spatial connection is quantum correlation. If this is right, the implications are profound. Space, the thing we move through, the thing that separates objects, the void between stars, isn't fundamental. It emerges from something deeper, patterns of quantum information and correlation. And if space is made of information, then the holographic principle isn't just about data storage. It's about the origin of reality itself. The three-dimensional world you experience, with all its distances and directions and room for things to happen, emerges from quantum information on a two-dimensional surface. Those patterns of information encode everything. Every event in the interior is represented in the entanglement structure of the boundary. The geometry of space itself is a kind of memory, a map of correlations that reflects every configuration of matter and energy that has ever existed. As you lie there in the quiet darkness, the space around you, between you and the walls, between Earth and the stars, might be woven from information encoded at the edge of the cosmos. And that information includes everything that has ever happened. The universe remembers, because remembering is built into the fabric of space itself. Now we can finally return to the puzzle that started this entire journey. The black hole information paradox. A black hole forms from a collapsing star. Over billions of years, it swallows matter and radiation, growing larger and more massive. All the information about everything that falls in every star, every planet, every atom, is trapped behind the event horizon. Then the black hole evaporates. Slowly, over unimaginable spans of time, it radiates away its mass as thermal, random Hawking radiation that carries no information about what fell in. Eventually, the black hole disappears completely. Where did the information go? The holographic principle provides the answer, and it's not what anyone expected. The information never fell into the black hole. Not really. Not at the deepest level of reality. Remember that in holographic physics, the bulk, including the black hole, emerges from information on the boundary. The boundary theory is the fundamental description. And in the boundary theory, there is no interior of the black hole. There's just a particular, very complex pattern of information on the boundary. When we say that something falls into a black hole, we're using bulk language, we're describing the process in terms of the three-dimensional interior. And that description is perfectly valid, perfectly accurate for most purposes. But it's not fundamental. The fundamental description is in terms of the boundary, and in that description, the information never goes anywhere. It was always on the boundary. It stays on the boundary. It evolves according to the ordinary rules of quantum mechanics, which preserve information perfectly. Here's another way to see it. Remember how a distant observer sees someone falling into a black hole? They appear to slow down as they approach the event horizon. Their clocks run slower and slower. They seem to freeze at the horizon, never quite crossing it. Their image getting dimmer and more redshifted but never actually disappearing. For years, this was treated as just a coordinate effect, a quirk of how distant observers measure time. The infalling person crosses the horizon in finite time by their own clock and falls on to the singularity. But holographic physics suggests that the distant observer's perspective is, in a deep sense, the correct one. The infalling object really does get smeared across the horizon. The information really does get encoded on the boundary. The interior journey, crossing the horizon, falling to the singularity, is a valid description from one perspective, but it's not the fundamental reality. This is called black hole complementarity. The same physics can be described in two different ways: as events happening in the three-dimensional interior, or as information being processed on the two-dimensional boundary. Both descriptions are valid. Neither is wrong. They're complementary perspectives on the same underlying reality, like wave and particle descriptions of light. When the black hole evaporates, the information doesn't need to escape from behind the horizon, because in the fundamental description, it was never behind the horizon. It was always on the boundary, always accessible, always evolving according to unitary quantum mechanics. The Hawking radiation does carry information away, but it's subtle, encoded in delicate correlations between early and late radiation that are almost impossible to detect. The information is preserved. Quantum mechanics is saved. This resolution took decades to work out, and some details remain controversial. There are still puzzles to solve, still aspects of the black hole interior that we don't fully understand. But the basic picture is now widely accepted by the physics community. Black holes don't destroy information. They store it. The event horizon is not an eraser. It's a memory bank. In 2004, Stephen Hawking himself publicly conceded the point. He had bet physicist John Preskill that information was genuinely destroyed by black holes. After decades of thought and the development of holographic ideas, he concluded he had been wrong. He paid off the bet with a baseball encyclopedia, a symbol of preserved information. Nothing is ever truly lost. Not to black holes, not to time, not to the universe. Information is conserved, encoded, preserved. The laws of physics guarantee it, including information about you. If the universe is a hologram with all information encoded on a distant boundary, an obvious question arises. Where is this boundary? Where is the surface that contains the cosmic memory? For Entanglement sitter space, the mathematical setting of the ADS/CFT correspondence, the answer is clear. The boundary is at spatial infinity. It wraps around the entire space, infinitely far from any interior point. But our universe is not Entanglement sitter space. We live in a cosmos with different geometry, different structure, different fate. So where is our holographic boundary? This question doesn't have a definitive answer yet. Extending the holographic principle from the idealized setting of ADS to the real universe is one of the major ongoing projects in theoretical physics. But there are several interesting possibilities. The first possibility is the cosmological horizon. Our universe is expanding, and that expansion is accelerating. Because of this acceleration, there's a limit to how far we can see or ever travel, no matter how long we wait. Light from beyond a certain distance, currently about 46 billion light-years, will never reach us. It's not that the light isn't trying. It's that space itself is expanding so fast that the light can never make up the distance. This defines a spherical surface around us, our cosmic horizon. Some physicists have proposed that this cosmological horizon is our holographic boundary. All the information about everything inside our observable universe, every galaxy, every star, every planet, every person, is encoded on this distant sphere. The three-dimensional world we experience is a projection from it. A second possibility focuses on time rather than space. Perhaps the holographic boundary isn't far away from us spatially. Perhaps it's far away temporally. Perhaps the boundary is at the very beginning, the Big Bang. In this picture, the universe is a holographic projection from the initial moment of creation. All of cosmic history, all 13.8 billion years of it, is encoded in the boundary conditions at the very beginning. The state of the Big Bang determines everything that follows, and the unfolding of time is like a hologram being played out. There's something appealing about this. We know that the current state of the universe depends on its initial conditions. The Big Bang set everything in motion, and the laws of physics have been evolving that initial state ever since. In a sense, all the information is in the beginning. A third possibility is that holography is local rather than global. Perhaps there isn't one cosmic boundary for the whole universe. Perhaps every region of space has its own holographic boundary. The surface of any volume you choose, a room, a planet, a galaxy, contains complete information about its interior. Holography applies at every scale, with boundaries encoding bulks all the way down. The truth is, we don't yet know which of these pictures is correct, or whether the reality is something else entirely that no one has thought of yet. Extending holography from the mathematical playground of Entanglement sitter space to the messy, complicated, expanding universe we actually inhabit is hard. It's one of the frontier problems in theoretical physics. But whatever the details turn out to be, the basic principle seems robust. Information about the interior is bounded by the area of the boundary, not the volume of the interior. The three-dimensional bulk emerges from two-dimensional data. Reality is holographic. And somewhere, whether at the edge of our observable universe, at the beginning of time, or around every region of space, there exists a record. A complete, perfect, permanent encoding of everything that happens within. As you lie there in the darkness tonight, you can imagine it. A distant surface, impossibly far away or impossibly long ago, containing a perfect representation of this very moment. The room you're in, the thoughts passing through your mind, the slow rhythm of your breathing as sleep approaches. All of it encoded, all of it preserved. The universe is a memory, and you're part of what it's remembering right now. Let's think carefully about what it means for information to be conserved. What exactly is being preserved, and in what sense? In physics, information has a precise technical meaning. It's not quite the same as knowledge or meaning or significance. It's more fundamental than that. Information is about distinguishability. A system contains information if it can be in different states that can be told apart. A coin has one bit of information. It can be heads or tails. A byte of computer memory has 8 bits, 256 possible states. A physical object like your body or a rock or a star has information in the quantum state of all its constituent particles. The positions, momenta, spins, and entanglements of every electron, every quark, every photon. All of this is information. It's what makes the object what it is, what distinguishes it from other possible arrangements of the same matter. The fundamental laws of physics, quantum mechanics, as far as we can tell, conserve information absolutely. The technical term is unitarity. Quantum evolution is reversible. If you know the exact state of a system at any moment, you can calculate what it was at any time in the past and what it will be at any time in the future. Information is never created and never destroyed. It can be transformed, scrambled, encoded in different forms, spread out over vast regions, but it never disappears. Now apply this principle to your life. Every moment you've ever experienced was a physical configuration of matter and energy. Atoms arranged in your body, neurons firing in your brain, photons entering your eyes. That configuration contained information. It was a specific state, distinguishable from other possible states. And if information is conserved, if it truly cannot be destroyed, then the information describing that moment still exists. Right now, it's not gone. It's been transformed, scattered, diluted, scrambled across the universe, and encoded in the quantum states of countless particles that have interacted with you directly or indirectly. But it's still there. In principle, it's preserved. The holographic principle makes this even more concrete. It says that all information about a region of space is encoded on its boundary. That boundary is a record, a complete description of everything that has ever happened within. So consider the boundary of our observable universe, wherever and whatever it is, contains a complete record of everything that has occurred in cosmic history. The Big Bang, the formation of the first stars, the emergence of life on Earth, your birth, your childhood, yesterday afternoon, all of it encoded, all of it preserved. Now, I want to be careful here. Preserved doesn't mean accessible. The information about your 10th birthday isn't sitting on a cosmic DVD somewhere, waiting to be played back. It's not stored in any retrievable form. It's been scrambled almost beyond imagination, mixed and entangled with all the other information about everything else that has happened, transformed by billions of interactions over billions of years. Actually reconstructing any particular past event would require knowledge and computation far beyond anything possible. For all practical purposes, the past is gone, but it's there, in principle, encoded in the structure of reality. This might seem like an empty distinction. What good is preservation if reconstruction is impossible? Why does it matter if information is technically still there but can never be recovered? I think it matters because of what it says about the nature of existence. We usually think of the past as gone, really, truly, fundamentally gone. The present moment exists. The future doesn't exist yet. And the past has ceased to be. It has vanished. It is no more. This is how we experience time, and it's natural to think this is how time actually is. But if information is conserved and encoded on boundaries, this picture is wrong. The past hasn't ceased to exist. It's encoded in the present. Every moment that has ever happened has left its mark on the physical state of the universe, and that mark persists. The universe doesn't just move through time, discarding each moment as it passes and replacing it with the next. The universe accumulates. Everything that happens becomes part of a permanent record, encoded, scrambled, practically inaccessible, but real. As you lie there tonight, drifting toward sleep, you are being recorded. Not by anyone, not intentionally, not in any way you could ever access or play back, but by the nature of physics itself. This moment, with all its details, all its sensations, all the particular thoughts passing through your mind, is being written into the structure of reality. And it will remain there as long as information is conserved, which is to say, as long as the laws of physics hold, this moment will be part of the universe. Forever. What does it mean for consciousness to exist in a holographic universe? This is speculative territory, far beyond what physics can currently answer with any confidence. We don't have a scientific theory of consciousness. We don't know how subjective experience arises from physical processes, or even if that's the right way to frame the question. The mystery of consciousness is one of the deepest unsolved problems in science and philosophy, but it's worth exploring, here in the quiet darkness, as sleep approaches. One straightforward possibility is that consciousness is simply information processing, complex information processing that happens to produce subjective experience as a byproduct. If this is right, then consciousness is encoded on the holographic boundary just like everything else. Your experience right now, the feeling of lying in bed, the sound of these words in your mind, the sensation of tiredness in your body, all of this is represented on some distant cosmic surface. In this view, there's nothing special about consciousness from the universe's point of view. It's information like any other kind. Complicated information, highly organized information, information that produces strange and remarkable effects, but information nonetheless. It gets processed and transformed and preserved according to the same rules that govern everything else in physics. But some thinkers have proposed more radical ideas. What if consciousness is related to the holographic nature of reality in some deeper way? What if awareness arises precisely from the relationship between boundary and bulk, from the process of information on a lower dimensional surface being projected into higher dimensional experience? This is purely speculative. There's no scientific evidence for it, but there's something poetically appealing about the idea that consciousness might be what it feels like to be a hologram. That subjective experience is the interior view, the first-person perspective, of information being projected from a boundary into a world. If something like this were true, consciousness wouldn't just happen to be encoded in the universe. It would be an essential part of how the universe works, a feature of holographic reality itself. Here's another way to think about it. Consciousness involves awareness, awareness of the world, awareness of yourself, awareness of being aware. It's a kind of reflection, a loop, a system that contains a representation of itself. And holography is also a kind of reflection. The boundary contains a representation of the bulk, and the bulk in some sense contains the boundary. In a holographic universe, the observer is not separate from the observed. The boundary encodes everything, including the minds that contemplate the encoding. We are part of the hologram, and we are also the hologram becoming aware of itself. There's something vertiginous about this recursion, something that feels almost mystical, even though it's grounded in physics. Whatever the ultimate relationship between consciousness and holography turns out to be, one thing seems clear: your conscious experiences are information. The particular pattern of neural activity that constitutes your awareness right now, the sights and sounds and thoughts and feelings, this is a physical configuration, and it has informational content. That information will propagate. It will influence your future brain states, your actions, your effects on the world. It will spread outward, interacting with other systems, becoming entangled with the rest of the universe. And through these interactions, it will become part of the permanent holographic record. In this sense, your consciousness, this moment of experience you're having right now, is being inscribed into reality. Not as a subjective feeling, perhaps. The universe doesn't store what it's like, but as information, as pattern, as structure. You are the universe experiencing itself, and the universe is recording the experience. We fear being forgotten. It's one of the deepest human anxieties. We build monuments and write books. We have children and hope they'll remember us. We carve our names into trees and benches and wet concrete. We create things that might outlast us, art, buildings, ideas, in the hope that something of ourselves will persist after we're gone. We want to matter. We want to be remembered. We want our existence to leave a trace. And usually it doesn't. Not for long. Most of the 100 billion humans who have ever lived have been completely forgotten. We don't know their names or their faces. We don't know what they thought or felt or hoped for. Their joys and sufferings, their daily lives, their entire existence. All gone, as completely as if they had never been. Even the famous are eventually forgotten. Give it enough time and every celebrity, every world leader, every name that everyone knows, all will be lost. Ozymandias, king of kings. But the holographic principle suggests something different. If information is conserved, if it truly cannot be destroyed, then nothing about any person who has ever lived is really gone. The information is scrambled and diluted beyond any possibility of recovery. No one could ever access it, but it's there. It exists. It's encoded in the physical state of the universe, preserved on cosmic boundaries. In this sense, everyone is remembered. Every life, every moment, every thought. Not by anyone, not by any consciousness holding the memories, but by the universe itself. The cosmos keeps perfect records. I find this comforting. Not in a religious way. This isn't about souls or afterlives or divine memory. It's just physics. But it's physics with a surprising implication. Nothing is lost. What you are, what you experience, what you feel and think and care about, it all leaves a permanent mark on reality. The universe is not indifferent to your existence. Couldn't be, even if it wanted to. Your existence changes the information content of reality, and that change persists. You matter cosmically, physically, literally. Your life has consequence in the structure of the universe itself. Maybe this is too abstract to be truly comforting. What good is being encoded on a cosmic boundary if no one can read the encoding? What does preservation mean if reconstruction is impossible? Is this really being remembered in any meaningful sense? I think it matters anyway. There's a difference between existing and not existing, even if no one is there to notice the difference. There's a difference between a universe where the past is truly erased and one where it's merely inaccessible. These are different physical situations, different states of reality. We live in the second kind of universe. The past is inaccessible to us, but it's not gone. It's encoded, preserved, part of the world. Your childhood happened, and that happening is part of the structure of reality forever. The people you've loved exist in the cosmos even after they die. Not as ghosts, not as spirits, but as information, as patterns that can never be fully erased. The moments of joy and connection you've experienced are inscribed in the universe permanently. Nothing is lost. Everything is remembered. Maybe that's enough. Let's step back now and consider the big picture of what we've learned tonight. We've journeyed from black holes to the edge of the cosmos, from quantum entanglement to the emergence of space, from a crisis in physics to a revolution in our understanding of reality. And we've arrived at a picture of the universe that is very different from our everyday experience. In this picture, space is not fundamental. It emerges from patterns of information and entanglement on a lower dimensional boundary. The three-dimensional world we move through, the space between objects, the distance to the stars, is a kind of projection. It's real and tangible and measurable, but it's not the deepest level of reality. In this picture, information is absolutely conserved, cannot be created or destroyed. Every event that happens, every particle that moves, every field that fluctuates, every thought that flickers through a mind, leaves a permanent record in the physical state of the universe. Information is scrambled and transformed, but it never disappears. In this picture, all that information is encoded on boundaries. The interior of any region of space, including the entire observable universe, is holographically represented on the surface that bounds it. The boundary is complete, contains everything. Put these together and what do you get? The universe is a memory. It's not a memory belonging to anyone. There's no cosmic mind holding these records. No divine consciousness preserving the past. It's more fundamental than that. Memory is built into the structure of physics itself. The laws of nature guarantee that information is preserved, and the holographic principle tells us where it's preserved. On boundaries, surfaces, edges. Everything that has ever happened is written in the cosmos. The Big Bang is there. The formation of galaxies and stars is there. The emergence and evolution of life on Earth is there. Human history, all of it, every civilization, every war, every love affair, every quiet afternoon, is there. And you are there. Your life, your experiences, your thoughts, your consciousness. All of it encoded. All of it preserved. All of it part of the universe forever. This is strange and beautiful and humbling. We're used to thinking of ourselves as temporary, brief flickers of consciousness in an indifferent cosmos, here for a moment and then gone without a trace. We're used to thinking that the universe doesn't care about us, doesn't notice us, doesn't preserve any record of our existence. But the holographic principle suggests something different. We're more permanent than we thought. Not eternal in the sense of living forever. Our consciousness will end, our experiences will cease, but eternal in the sense of never being fully erased. We leave traces that cannot be removed. We make marks that cannot be undone. The universe carries us with it. Always. If the holographic principle is true, it tells us something profound about the ultimate nature of existence. For centuries, we've thought of reality as made of matter. Particles, atoms, molecules, physical stuff with mass and solidity. Physics began as the study of material objects and their motions. Balls rolling down inclined planes, planets orbiting the sun, atoms bouncing off each other. Even as physics progressed to more abstract concepts, fields, waves, quantum states, we still thought of these as the fundamental stuff of existence. There's the electromagnetic field, and it fills space. There are quantum fields for electrons and quarks, and particles are excitations of these fields. Reality is made of something, and that something is physical and substantial. But the holographic principle suggests that this picture is wrong. Matter isn't fundamental. Even space isn't fundamental. What's fundamental is information. Information is the basic currency of the cosmos. Everything else, particles, fields, forces, space, time, emerges from the way information is organized, processed, and encoded. The universe isn't made of stuff. It's made of bits. This perspective is sometimes summarized in a slogan coined by the physicist John Wheeler. It from bit. The it, physical reality, everything we can see and touch and measure, comes from the bit, information. Physics is, at its deepest level, information theory. If this is right, it transforms how we think about existence. What does it mean for something to exist? Not to be made of matter, matter is secondary. To exist is to be represented in information. A thing exists if there's information about it, if it's encoded somewhere in the structure of reality. And this suggests something remarkable about consciousness. Consciousness is, whatever else it is, information processing. It's patterns of activity in a physical system, your brain, that represent the world and represent themselves. It's information becoming aware of itself. In a universe where information is fundamental, consciousness isn't some odd byproduct of matter, some strange epiphenomenon that happens to emerge when atoms are arranged just right. It might be closer to the heart of reality than that. Information, awareness, representation, encoding, these might be among the most basic features of existence. You're not just in the universe. You're not just made of universe stuff arranged in a complicated pattern. In a deep sense, you are the universe. You're a particular configuration of the universal information, a specific pattern that has become complex enough to know itself. The cosmos is not a stage on which we perform. It's not a container that holds us. We are expressions of it, local concentrations of cosmic information that have achieved self-awareness. And when you see it this way, the holographic principle isn't just about data storage or the mathematics of black holes. It's about what we are and what existence is. It's about the relationship between mind and cosmos, information and reality, the observer and the observed. We are patterns in the universal information. We are the universe encoding itself, knowing itself, remembering itself. We should be honest here near the end about how much we don't know. The holographic principle is well established for anti-de Sitter space. The AD/CFT correspondence is one of the most important and most rigorously supported results in theoretical physics of the past 3 decades. In that setting, holography isn't speculation, it's proven mathematics. But extending holography from that idealized setting to the real universe is still a work in progress. Our space-time doesn't look like anti-de Sitter space. It has different curvature, different geometry. It's expanding and probably infinite. We don't have a rigorous AD/CFT-like correspondence for our cosmos. We have strong theoretical reasons to think that something similar applies, but we don't know the details. We don't know for certain that our universe is holographic, or where its boundary is, or how the encoding works. We also don't understand consciousness. Not really. We know a lot about the brain, which regions are active during which tasks, how neurons fire and connect, how damage to certain areas affects certain abilities. But we don't understand how physical processes give rise to subjective experience. We don't know why there's something it's like to be you, why the information processing in your brain is accompanied by awareness, by the felt quality of experience. This is sometimes called the hard problem of consciousness, and no one has solved it. So when we talk about consciousness in a holographic universe, we're combining one partially understood thing with another barely understood thing. We're speculating, not explaining. And we don't know how to reconcile quantum mechanics with general relativity. These are the 2 pillars of modern physics. Quantum mechanics describes the very small, general relativity describes gravity and the very large. Both are extraordinarily well-tested, and they're fundamentally incompatible. We don't have a theory of quantum gravity. We don't have a complete description of how nature works. The holographic principle might be part of the answer. String theory and holography and related ideas might eventually lead to a unified understanding. But we're not there yet. We're still working on the foundations. These are hard problems. They might take decades more to solve. They might require ideas that no one has had yet, conceptual breakthroughs that will seem obvious in retrospect but are invisible to us now. But I think there's value in contemplating these questions anyway, even without final answers. There's value in lying in the dark and letting strange ideas wash over you, feeling their weight and their implications, even if you can't tie them up in neat conclusions. The universe is mysterious. That's not a failure of science. It's a feature of reality. There's more to existence than we currently understand, possibly more than we will ever understand. Living with mystery, holding questions without demanding answers, is part of what it means to be a conscious being in a cosmos far larger and stranger than our minds evolved to comprehend. Tonight, as you drift toward sleep, you're a pattern of information in a possibly holographic universe, thinking about what it would mean for the universe to be holographic. That's remarkable. That's extraordinary. Whatever the answers turn out to be, the fact that you can ask the questions is something to appreciate. We're nearing the end of our journey now, and I want to bring us back to where we started. The universe remembers. It remembers the Big Bang, that initial moment of unimaginable heat and density 13.8 billion years ago. The information from that primordial fireball is still present in the cosmos, encoded in the cosmic microwave background radiation that fills all of space, in the distribution of galaxies across the sky, in the abundances of the chemical elements. The universe remembers the first stars that formed, a few 100 million years after the beginning, massive, hot, short-lived, forging heavy elements in their cores and scattering them into space when they exploded. The information about those stars is still here, in the composition of later generations of stars and planets, in the atoms that make up everything we see. The universe remembers the formation of galaxies, the slow gravitational gathering of matter into vast rotating disks and spheres of hundreds of billions of stars. It remembers the formation of our solar system 4.5 billion years ago, from a cloud of gas and dust enriched by countless stellar explosions. It remembers the formation of Earth, the emergence of life, the long, slow evolution from single-celled organisms to the riot of complexity we see today. And the universe remembers you, your birth, your childhood, every day you've lived, every person you've loved, every thought you've had, every moment of joy or sorrow or boredom or peace. All of it has left its mark on the physical state of the universe. All of it is encoded somewhere in the quantum states of particles, in the patterns of light that have radiated outward from you at the speed of light, in the holographic boundary, wherever it is that preserves the information of everything that happens within. All of it is permanent. This isn't memory as we usually think of it. No one is actively remembering. No consciousness is holding these records. No system is indexing and organizing the cosmic library. It's more fundamental than that, and in a way more impersonal. It's simply the conservation of information, the impossibility of true erasure. But it means something. It means the past is real in a way we don't usually appreciate. It means your life has a kind of permanence that survives the moment. It means, in a very literal, physical sense, that nothing you experience is ever truly lost. The night is deep now, and perhaps your thoughts have begun to soften and blur at the edges, the way they do when sleep approaches. You've traveled a long way tonight, from the event horizons of black holes to the distant boundaries of the cosmos, from the paradoxes of quantum mechanics to the emergence of space from entanglement, from the crisis that threatened to break physics to the revolution that is remaking our understanding of reality. These are big ideas, strange ideas, hard to hold all at once, hard to keep in focus. They strain against the limits of language and intuition. They ask us to accept that space is not what it seems, that reality is not what it seems, that we ourselves are not quite what we seem. Let them go now. You don't need to hold on to them. Let them settle into the background of your mind, like sediment drifting to the bottom of a still pond. What remains is simpler. You are here. You are aware. And that awareness, that presence, is part of the universe's permanent record. Tomorrow you'll wake with the day's concerns and tasks and distractions. You probably won't think about holographic boundaries or the conservation of information. You'll move through the world in the ordinary way, taking space and time for granted, experiencing yourself as a person in a place. That's fine. That's how we live. But maybe, in some quiet moment, you'll remember this. Nothing is lost. The universe carries everything with it, always, including you. Maybe you'll look at the night sky and remember that somewhere out there, or everywhere out there, is a record of this moment, this night, this life. Maybe you'll look at a loved one and remember that they, too, are inscribed in the cosmos, permanent and indelible. There's something restful in that, something that makes it easier to let go. If everything is preserved, there's nothing you need to clutch at. You can release this moment, this day, this chapter of your life, knowing that it's already saved, knowing that it can never be taken away. So release it. Let your breathing slow and deepen. Let the small tensions in your body soften and melt. Let your thoughts drift and fade, one into another, losing their edges, becoming vague and gentle and quiet. The cosmos holds you. It always has. It always will. Sleep now, knowing that you're part of something permanent, something vast, something that remembers. There's something you need to know about the universe. It remembers everything, including this moment, the darkness around you, the weight of your body on the bed, the sound of these words in your mind, the last thoughts drifting through your consciousness as sleep finally arrives. All of it encoded, all of it preserved, all of it part of the permanent record. You're not separate from this memory. You don't stand outside it looking in. You are this memory, one particular pattern of cosmic information among countless others, but irreplaceable, unique, eternally part of the whole. Tomorrow the world will seem solid and three-dimensional again. Objects will have depth, space will have distance, and the holographic boundary will feel impossibly remote, if you think about it at all. But it's always there, always encoding, always preserving. The record is always being written, and nothing is ever lost. Sleep well. You are remembered. Good night.